All right, so we're in the second part of 12.4.
Oh wait, stop. It's Tuesday.
All right. So what we're doing here is we're going to extend kind of what we talked about with projectile motion. So we're thinking of R of t, our vector valued function, as describing a position vector, and our parameter is time. So we're thinking of our vector valued function as describing the motion of something. What we're interested in today is we figured out the other day how to find a unit tangent vector that is tangent to our curve at a particular point, points in the direction of increasing parameter, and we figured out also how to find a unit normal or principal unit normal vector, which is orthogonal to our unit tangent vector and points in the direction of the concavity of the curve, or in the direction that the curve is turning. What we want to do is today is break down acceleration into a component that's tangent to the curve and a component that is normal to the curve. And we talked about it briefly on Friday. If we're thinking of R of t as a position vector, what would the tangential component of acceleration do to our motion? Speed up or slow down, right? Because it's going to be in the same direction, or it's going to be tangent to the curve. So that's telling us, are we speeding up? Are we slowing down? And then the normal component of acceleration. What's the normal component of acceleration? Perpendicular. So it's perpendicular direction. So it's going to be what changes the direction of motion. So we're looking at acceleration. We're breaking down acceleration into a component that speeds us up or slows us down, and a component that changes our direction. So we said, when we talked about our unit tangent vector, we said that t is r prime, and I'm going to drop the t notation here over r, over the magnitude of r prime. This was our unit tangent vector. And we're going to call V we're going to call it the velocity vector. And the magnitude, the speed, scalar v, is going to be the magnitude of our velocity vector.
Is it a V or an R?
This is a v.
Is it inside?
This is a v also. So this is scalar v, this is vector v. So this is our velocity vector, this is our speed. So using this notation, we can say that our unit tangent vector is v over the length of v. So we're just changing our notation a little bit here. And if I rearrange this, I can say that my velocity vector, so my velocity vector is the magnitude of my velocity times the unit tangent vector. So this is going to be the start. This is where we're going to start our analysis. We're going to look at the acceleration starting from here. So to find the acceleration from the velocity, what do I do? Derivative, right. So we're going to differentiate. And I'll say to get acceleration. Need to move this over so I have enough room on my page. So we're going to differentiate this quantity to get our acceleration. So we're going to say that d dt of the velocity is our acceleration, and that's going to be, I'm going to use the product rule on this quantity. That's going to be the derivative of the magnitude of the velocity with respect to time times our unit tangent vector plus our unit tangent vector magnitude, our velocity vector magnitude times the derivative with respect to the time of our unit tangent vector. So we're just using the product rule here. And so in this first term, we have a component of our acceleration that's just a multiple of the unit tangent vector. So right here is our tangential component of acceleration. We need to work with this a little bit more to get this in just a slightly different form. So I'm going to multiply here by a convenient form of 1. So I'm going to say that my acceleration vector is, we're going to leave this one alone. Plus the magnitude of my velocity here, and I'm going to multiply this dt by the magnitude of t prime over the magnitude of t prime. And then rearrange a little bit. So this equals ddt of my speed times my unit tangent vector plus the speed times t prime dt, the derivative with respect to time of the unit tangent vector is just t prime. So I get t prime over the length of t prime, the magnitude, times the magnitude of t prime. Well, what's t prime over the length of t prime? That's our principal normal vector. So now I can say that my acceleration is the derivative of the speed with respect to time times our unit tangent vector plus the speed times the magnitude of t prime times our principal unit normal vector. And from this we say that the acceleration, finally, is a sub t times our unit tangent vector plus a sub n times our unit normal vector, where a sub t is our tangential component of acceleration, is the derivative of our speed with respect to time, just like we would expect. And a sub n is the speed times the magnitude of t prime. So here are two components of acceleration. We have a component that is a multiple of our unit tangent vector, and a component that's a multiple of our unit normal vector. So this was our goal, was to be able to express acceleration as something that is tangent to our curve and something that's normal to our curve. Any questions on our analysis?
Yeah, one quick one.
Yes.
So when you have t prime over the magnitude of t prime up there, yes, times t prime. So where is the unit normal vector in that?
T prime over the magnitude of t prime was our definition of the principal unit normal vector.
Oh wait, no. So
This quantity.
That wasn't the one I told. Sorry, right before that. How did we get to that point? That's what.
Here,
Yeah.
I just we multiplied by a convenient form of 1.
Okay.
So we know that the derivative with respect to time of t
Oh, it
is t prime.
okay, never mind.
So that's where this t prime comes from, and so then we know that t prime over the length of t prime is our unit normal vector. So we wanted to get to that unit normal vector.
All right, thanks.
Okay. All right. So what we've accomplished two things here. So our analysis, we accomplish two things. And the first one, well, they're both kind of important. What we've accomplished is that the first is that the quantities that we get for a sub t and a sub n are our tangential and normal components of acceleration. That's what we were after. The second thing that we accomplish is that since our acceleration vector as a function of time, since we can write it, since it can be written as a linear combination of our unit tangent vector and our unit normal vector. Anybody know what this guarantees us about our acceleration? So our acceleration is some quantity times our unit tangent vector, plus some quantity times our unit normal vector. What kind of geometric thing do the unit tangent vector and the unit normal vector define in space? A plane. They're two vectors. They define a plane. So since our acceleration could be written as a linear combination of these two vectors, what does that guarantee us about the acceleration? It has to be in the same plane that is defined by the unit tangent vector and the unit normal vector. So our acceleration has to be in the plane defined by t and n. So this means that that if our particle is doing some kind of crazy motion, that the acceleration is always going to be in this plane defined by t and n. So what this allows us to do, and what we normally want to do, let's look back at our expressions for a sub t and a sub n. So we have an expression for a sub t that has to do with the velocity, and we have this a sub n that has to do with the speed and the magnitude of speed and the magnitude of the unit tangent vector. What we usually want to do is be able to express this in terms of r prime and r double prime. So the fact that these are coplanar, all these quantities are coplanar, lets us do something else. So let me draw a picture here. If this is our motion here, so this is r of t. We have, I'm going to draw in my acceleration vector. I'll do that in blue. So let's say at this point our acceleration vector looks something like this. And I'm just making these up. I don't know that this is necessarily what it would physically look like. So we're going to say this is my acceleration vector. And we're going to have our unit tangent vector here. So that's my unit tangent vector. And my unit normal vector I'll do in green here. And what I'm going to do is project this onto t and project this onto n, like so, my acceleration. Well, this length, since t and n are unit normal vectors, this length here is a dot t. And this length here is a dot n. So since these are coplanar, we can look at these components. And I'm sorry, I put these backwards. This quantity would be a dot n. We're projecting onto n. And this would be a dot t. That's the component of a in the direction of t, and this is the component of a that we're projecting onto n. So since they're coplanar, we can look at these quantities in terms of these dot products, and this allows us to simplify or come up with a process for finding a sub t and a sub n. So usually we want to express a sub n and a sub t in terms of our position vector, our velocity vector, and our acceleration vector. So what we do is we look at these dot products, and we analyze, we manipulate these dot products to come up with these expressions. Now I'm not going to go through, the derivations are kind of long, and I don't want to do them in class. I'm going to do them as a separate set of notes, and I will post them on the website. I strongly suggest that you at some point before the end of the chapter, you watch those derivations for how we get these expressions for a sub t and a sub n in terms of r prime and r double prime. I just don't want to do them all in class. But they come from looking at, because these quantities are coplanar, we can look at these dot products. We can also look at a cross product and come up with these expressions for a sub t and a sub n in terms of r prime and r double prime. So I'm going to skip the derivations in class, but I will do them separately and post them to the website. What the results, we'll just take the results in class, the results of those derivations, the results of these conclusions are and we'll say one more time that my acceleration vector, our acceleration vector with respect to time, is a sub t times our unit tangent vector plus a sub n times our unit normal vector. We can break it down into tangential and normal components. Directly from here, if we know our unit tangent, our tangential and normal components of acceleration, this gives us a shortcut to finding our principal unit normal vector, which we saw can sometimes be really algebraically intense. So we can say that n, if we have all these other quantities, our principal unit normal vector is our acceleration vector minus a sub t times our unit tangent vector divided by a sub n. So if we can calculate these quantities, we can usually calculate the unit tangent vector relatively easily. We can find a way to find a sub t and a sub n relatively easily. That gives us a shortcut to find our principal unit normal vector. A sub t is the derivative with respect to time of our speed, the magnitude of the velocity vector. It equals a dot t, and what we didn't derive, but I will at a later time, is v dot a over the length of v. So this gives us a way to find our tangential component of acceleration just from the velocity and the acceleration vectors. A sub n, our normal component of acceleration, is from our first, just from taking derivatives, is the speed times the magnitude of t prime. This is our acceleration dot n, and this is the magnitude of v cross a over the magnitude of v. And this also equals the square root of the magnitude of the acceleration squared minus a sub t squared. So these two quantities are ones that come from the derivations that we're not going to do in class. And these are the ones that we're normally going to compute with if we want to find our tangential and normal components of acceleration. But it takes about 15 minutes of work to get to these. So any questions so far? All right, let's look at a couple of examples. Let's start with an easy one. We have r of t equals t squared I plus 2tj. And our problem asks us to find our unit tangent vector, our unit normal vector, tangential component of acceleration, and the normal component of acceleration. And we're looking at t equals 1. So we have to find some derivatives here. So r prime. So v or r, we can say v or r prime. So I'm going to say v. What's our velocity vector here? 2ti plus 2j. And the magnitude of the speed, or I'm sorry, the magnitude of the velocity, the speed, is going to be what? Square root? 4t squared plus 4. So our prime, or v, the velocity at time 1, is going to be 2 square root 2. I plug in 1 here. Sorry, that's going to be our speed. Our speed at time 1 is 2 square root 2. So our t prime, or I'm sorry, our unit tangent vector at time 1 is just the speed, or the velocity over the velocity divided by the speed. The velocity divided by the magnitude of the velocity at time 1. So that's going to be 1 over 2 square root 2 times 2i plus 2j. So there's our unit tangent vector at time equals 1. We evaluated at t equals 1. So we didn't have to find a general expression, we're just looking for it at this one particular time. So looking back at our formulas, to find our a sub t, we're going to do, I'm going to use v dot a over the length of v to find a sub t. So I need my acceleration vector. Our double prime of t is going to be what? 2i. And our double prime, I'm going to say the velocity at 1 dot the acceleration at 1. I'm going to take the dot product of the velocity at time equals 1 and the acceleration at time equals 1, and I'm going to divide it by the magnitude of the velocity at time equals 1. That was our expression for a sub t. And when I do this, I get 2i plus 2j dot 2i over 2 square root 2. And I get square root of 2. So my tangential component of acceleration is square root of 2. And whatever my units would be, so it would be square root of 2, whatever meters per second squared. So there's my tangential component of acceleration. For this one, we'll say that a sub n, our normal component of acceleration, we're going to use, I'll use this expression for a sub n. So we're going to say that a sub n is going to be v cross a magnitude over the length of v. So for what we have here, it's going to be r prime, and we're looking at time equals 1. R prime of 1 cross r double prime at 1, the magnitude of that, over r prime at 1, and the magnitude of that. So my cross product, r prime at 1 cross r double prime at 1, and that's going to be our determinant ijk 2, 2, 0 and 2, 0, 0. And when I calculate this out, I get minus 4k hat, and the magnitude is just 4. So now I can just plug that in and say that a sub n equals 4 over 2 square root 2, which just gives me square root 2. So now I have 3 of the 4 quantities that we wanted. There's my unit tangent vector, there's a sub t, and here is the normal component of acceleration. We want to find the principal unit normal vector at time equals 1. So for that one, I'm going to say that n, our principal unit normal vector, is the acceleration at time equals 1 minus a sub t times the unit tangent vector at time equals 1 divided by a sub n. This is going to be way easier than trying to figure out t prime over the length of t prime. So I'm just plugging in my quantities here. So I get 2i minus square root of 2 times square root of 2 over 2i plus square root of 2 over 2j, all divided by square root of 2. And when I simplify that all out, I get square root of 2 over 2i minus square root of 2 over 2j. And that is our unit normal vector at time equals 1. So what do you notice about these calculations? They're kind of tedious? Yeah. Tangential and normal components of acceleration, the calculations are on the tedious side. I will admit that. But this expression, much easier than usually much easier than trying to find t prime over the length of t prime. So if we can go through this analysis to find our unit normal vector, usually easier than finding t prime over the length of t prime to find our unit normal vector. And let me go back here really quickly. This expression for a sub n is often easier to calculate than the cross product, than this cross product. So don't forget about this nice little expression to find a sub n as well. Because a sub t is relatively easy because we're just doing a dot product. So a sub n comes from that pretty easily. And then this is usually is easier to calculate than our other expression for the unit normal. Yes.
Is it included?
I will take a look. I can't remember. All right, I'm not going to do another example because it's just more calculating derivatives and dot products and cross products and magnitudes. Any questions? Okay. Homework. And I'll take a look at the quiz. There you go.